Hi guys, welcome to today's tutorial. We are going to look at the 2020 examinations on the Achievement Standard 91164, which is the structure and bonding standard. And just before we start, 70% of the people that watch my videos aren't subscribed. So if you can just, take a moment and subscribe and leave a like, that'll be greatly appreciated. And as we're heading towards the exam season, if you could spread the word. If you have people that are struggling in level 1 science or level 2 or level 3 chemistry, just send them my way, and hopefully they can find enough help so they can do well for the upcoming assessments. Okay, so let's get started. So 2.4 examination. So first set of questions is looking at the solid section. So when you have these type of questions, pretty straightforward, especially if you have watched my previous years of the examinations. And by the way, I'm going through the entire exam in one video, and I'll put the chapters in the description, so if you can just, if you like say need help with question 3, you don't want to watch question 1 and 2, and you can just skip to that part that you need. Okay, so for these type, just remember, if you have a metal, remember this is your periodic table of elements which you get given, and then you have that staircase. On the left hand side you have metals, on the right hand side you have non-metals. So if you have something that's bonding, like say for example Cl2, you have a non-metal bonding with a non-metal, you have a molecular type of solid. And if you have a metal bonding with a non-metal, this is an ionic type of solid. If you have a metal just on its own, like say for example if I just have magnesium, this is metallic solid. And then if you have silicon dioxide, so this is one of the examples, if you have silicon dioxide, SiO2, graphite and diamond, these 3 are your giant covalent network. Okay, so don't write GCN, just write giant covalent network because I don't have a lot of space. The type of particles, the giant covalent network is made of atoms, molecular solids are made of molecules, and ionic solids are made of ions, and metallic solids made of atoms. Okay, and this is covalent bonding, and Cl2 is intermolecular forces, or your teachers taught you Van der Waals force of attraction. They're all okay. Anything's, either of the 3, either of the 2 is okay. KCl is ionic bonding, and magnesium in this case is metallic bonding. That wasn't part of the question, I just put it here. Okay, so the key part again is to look at the structure, look at the chemical formula, because if you can figure out what type of molecule, what type of solids it is, and then you can just pretty much learn everything for an easy achieved. Okay, so next part, so the electrical conductivity of silicon dioxide and potassium chloride is different. Okay, so silicon dioxide, like we said, is a giant covalent network. Giant covalent network are the only giant covalent network solids that conducts electricity that you know of is graphite. So it doesn't conduct electricity at all. KCl is an ionic solid, so it doesn't conduct electricity as a solid, but it does conduct electricity when molten. So the key idea is that you need to tell us what type of bonding they have. So this is covalent bonding. So for anything that have that conducts electricity, electrical conductivity, you require one of these 2 things. You need free moving electrons or free moving ions, one of the 2. Okay, so if you have SiO2, which is covalent bonding, and what that is that each Si is bonding to 4 oxygens, and each oxygen is bonding to Si, and that just extend onto a massive structure, and there's no free moving electrons and there's no free moving ions. So silicon dioxide will not conduct electricity because it's a giant covalent network solid. It's made of covalent bonding. There are no free moving ions, electrons, therefore they cannot carry charges, therefore it doesn't conduct electricity. But instead of now we're looking at KCl. KCl is made of the positive K, so I'll just represent K with the positive, and then this K is surrounded by negatives, so it's kind of like this. you have that three-dimensional structure, and that just extends on and on, so I'm not going to draw the rest. So what that does is that this just it's a three-dimensional lattice structure, so you have the positive surrounded by negatives, and then the negatives surrounded by positives. So these are ions, so KCl is made of ions, so you have positive and negative ions, but when they are a solid, they are not free moving because they are locked in this three-dimensional structure. They can't just leave and carry a charge because they're surrounded by other charged ions, so that attraction is quite strong. But when molten just means if I apply a lot of heat energy and this particular solid is molten, so that means the positive ions and negative ions are now free flowing. They can move around whenever they want, go wherever they want, and then they can carry charges with them. Okay, so this is your very typical excellence type of question. So remember, electrical conductivity requires the presence of charged particles, so they're free to move, so you can mention free moving electrons or ions. And silicon dioxide is a covalent network, three-dimensional lattice. So there's no charged particles in both liquid or solid, so it can't conduct electricity. And potassium chloride has ionic compound because the ions are fixed in that, are locked in the lattice structure, so they can't move. If they can't move, they can't carry charges. But when molten, the bond is broken, they are free to move, they can conduct electricity. Okay, so it's a very, for these type of questions, you always want to talk about what type of solid they are. Like, look at the physical property. Then for each individual solids, talk about what type of solid they have, what type of bonding they have, and why do they show this particular physical property. Okay, so let's look at the next one. KCl is soluble in water, but chlorine gas is not readily soluble in water. So use your knowledge of structure and bonding to explain the difference in solubility. So solubility, again, is one of those ones that's becoming more and more popular. So again, if you come from my previous year's exams, so yeah, you probably, I mean, I would strongly recommend for you to probably go, if you're starting to learn the exam, like trying to prepare for the exams, I would recommend you to go to the 2018 one first, because that's when I spend the most time like breaking down each individual concept. And the more I did, the more I was repeating myself, because you will find the videos to be, the questions to be very, very similar. So the answers are quite similar as well. So I may not be as thorough as the previous years, because it's pretty much the same thing. Okay, but for anything to dissolve, the difference in solubility. So for anything to dissolve, you have to understand, why do things dissolve? It's because if you mix, let's say if you mix water, let's say water, if you have water molecules, which looks like that, this is water molecules. Actually, let's just use letters. Letters is easier. H2O, H2O, H2O. And remember, this is a polar molecule, so H2O, this side is more positive, this side is more negative. So actually, let's do it this way. And this side is more positive. So when you have these water molecules that are, hanging, like you learned this more in year 13. Look at this more detailed intermolecular force. But what happens when you put these guys together? Because you can see that this O is negatively charged, slightly negatively charged, and that can interact with the positive charges of the neighboring hydrogen molecule, hydrogen from the water molecule. So this is your water. So as a water molecule, they have quite strong intermolecular forces because the water molecules like to hang out with each other. And if you have the Cl2 coming along, like you have a chlorine bonding with the chlorine, chlorine bonding with the chlorine, these guys are non-polar, so they don't have the slight positives or slight negatives. So imagine if they're like, if you mix them together, the Cls and the Cls go, you guys are pretty cool, but the H2Os don't want to hang out with the Cl. They're more than happy to hang out with each other. They don't like the chlorines because they're not charged, so they're not going to mix with them. So the solubility depends on the strength of the force of attraction before you mix them together and after you mix them together. Because if you have the existing molecules together, and so there's a force of attraction between the existing molecules before you mix them together. And after you added them, mix them together in the same container, if the new force of attraction between, like say for example, if H2O and HCl, and you just go, all right, not HCl, Cl, you go, all right, do these guys want to hang out with each other? No. So that means this new force of attraction is weaker than the existing force of attraction, so they're not going to dissolve. Okay, so why do something dissolve is that the new force of attraction, the new combination, is stronger than what they had previously, and they want to do that. So they say you should include a diagram to show you, illustrate the answers for KCl. So KCl looks like this. This side is positive, this side is negative, because your K will break down to K plus and Cl minus. And when you dissolve this in water, when you put KCl in water, they will separate. Why do they separate? Because they are soluble. Why are they soluble? It's because water molecules are polar. Okay, so what they do is that they will surround, so remember the H's are slightly positive. So what the H's will do, they will surround the negative ion, which is chlorine. So instead of the chloride. So instead of the chloride ion hanging out with the K plus, it's now separated from the K plus, and it's being surrounded by the positive ends of these H plus molecules. Okay, and it wants to. So this is why it's soluble, because this force of attraction is stronger than the K plus and Cl minus force of attraction, and that's why it dissolves. Okay, so with the K1, it's going to look exactly the same, but it's going to look a little bit different because K is positively charged, so it's going to get surrounded by the negative end of the water molecule, which is the oxygen. Okay, so the oxygens are slightly negative, slightly negative, slightly negative, oops, slightly negative, slightly negative. So, oops. So this force of attraction again is stronger than the K plus and Cl minus force of attraction. Okay, so here we go. So why do they dissolve in water? Because the negative end of the water molecules attract to the K plus, and the positive end of the water molecule attract to the Cl minus, like the diagram. So this causes them to be surrounded by water molecules, and the solid dissolves. Okay, so the key thing that you need to remember is that the force of attraction between the ions of water is strong enough to overcome the existing bond. In this case, it's ion bonding. Okay, so the non-polar molecule, which is a chlorine, they can't do that because they don't have a charge, so they can't break the existing force of attraction. So they're much happier just to hang out on their own, because they can't really achieve that next level of breaking that the water's force of attraction. So overall, it stays separate, so they're not soluble. Okay, so this is a very becoming more popular, because I've done the past year's exams quite every single year, and this is definitely becoming more and more popular. Okay, so hopefully that makes sense. But if you go to either 2019, 2018, one of those exams, they have exactly the same question. So just make sure you understand what's happening, and then hopefully produce the same sort of thing in the exam. All right, next part. So this is question 2. All right, question 2. So CS2, let me draw this Lewis diagram. So for I'm using a highlighter. For CS2 looks like this. So I have my method of doing it, which is that. So you just write down how many valence electrons they have. So which is 4, 6, 6. How many do they need? 8, 8, 8. So this, I need 24. I only have 16. 24 minus 16 is 8 electrons. 8 electrons means 4 bonds. So that means carbon needs to have, so there are 4 bonds. So this is what we're trying to figure out. 4 bonds, 1, 2, 3, 4, and then you complete all the elements to make sure they have 8 electrons around them. But by now you should have done organic chemistry, and you should know that carbon always need to have 4 bonds, nitrogen always have 3 bonds, carbon always have 4 bonds, hydrogen only bond once, fluorine only bond once, chlorine only bond once, and oxygen bonds twice. So you should know these already. So this method, it can be a little bit redundant, but it's always good to know if you're struggling. Okay, if you aren't so good at organic, you can just always rely on this method. Okay, so this is linear because I have got 2 regions of electron density around the central carbon atom, and they are as far away as possible, 180 degrees linear. Okay, so NOCl will look like this. That looks ugly. Let me draw it like this. NOCl. That's 1, 2, 3, 4. And this is also not linear. This is a bent shape. So how did I know how to draw NOCl that quickly? So again, because I know nitrogen always needs 3 bonds, oxygen always needs 2 bonds, and chlorine always needs 1 bond. That's why you never double bond the chlorine. You never ever double bond the chlorine, because chlorine only needs to gain 1 electron to form a stable compound. So if you want to use this method, you can. I can just show you. This is 5, 6, 7. 8, 8, 8, 24, this is 18, so 24 minus 18 is 6 electrons, 6 electrons, 3 bonds. That's why you have 3 lines here, 3 bonds. But just make sure that you know that you double bond the oxygen and single bond the chlorine, and that's just from organic, because oxygen needs 2 electrons, oxygen is 2, 6, so it needs 2 electrons to form a stable outer shell. That's why you need 2 electrons. Okay, now CH2F2 is even easier, so I'm not going to show that method anymore. CH2F2. Don't forget to put your oops, I'm not on the hydrogen. So this is tetrahedral. Okay, Lewis diagram, nice and easy. Next part. They have the same number of atoms in the formula but at different shapes, and bond angles justify the bond angle. Okay, so this is kind of like a Meredith type of question. So first thing first, you look at your central atom. Central atom is carbon. This has 1, 2, 3. So for CHO, this has 3 regions of electron density. And what they want to do is that they want to position themselves as far away as possible to minimize repulsion. Okay, so that's probably in the answer, so I'm not going to write all that down. So again, if you didn't catch that, these regions of electron density, because they're all negatives, they want to position themselves as far away as possible to minimize repulsion, and that will give them a trigonoplanar shape. If you look at NF3 nitrogen is a central atom. So this has 1, 2, 3, 4. So this has 4 regions of electron densities, so they will repel each other as far away to minimize repulsion. And that lone pair of electron, which is this guy up here, this lone pair will actually exert more repulsion because it's much, it's closer to the nitrogen and resulting in more repulsion force. Okay, so similar sort of things. You can see CH2O has 3 regions of electron density, clouds, whatever you want to call it. They want to minimize the repulsion, maximize separation, position themselves as far away as possible, minimize repulsion, therefore trigonoplanar. Okay, and F3 has 4 regions, and the same thing. They take the tetrahedral. Now they say geometry. I personally like to say they take a tetrahedral arrangement. Okay, so they have a tetrahedral arrangement because if you look at it, it looks like this. So 1, 2, 3, 4. It has a tetrahedral arrangement because you've got 4 electron densities. But this lone pair, this cannot be observed, so you can't see it. So if you can't see it, that wouldn't contribute to your final shape, would it? Because you can't see it. But then it is there to cause a repulsion. So that's going to push this guy down, push this guy down, push this guy down, but you can't see it physically. So the actual shape will be trigonopyramid or trigonopyramidal because of the 4 things, and one of them cannot be observed. Okay, next one. This polarity questions are guaranteed to come up as an excellence question, so just learn it. Okay, a molecular compound consists of 2 different elements, XZ, containing 3 atoms. Its form is ZX squared, ZX2. The elements have different electronegativity, so that's important. Depends on the identity of the elements. It could be either polar or non-polar. Okay, so we have a very different type of question. So they ask you for the proper shape. So the best way, if you look at these type of questions, you don't know what to do. The best way to actually give the Z and X, give them something like, say, if you have CO2 you have SO2. These are the very two common examples that we've done in the past. SO2, so if you have different electronegativities, so what that means is that, actually because you might not remember SO2, CO2, let's teach you this way. So if you know they have different electronegativities, so that means the bonding between Z and X, one of them will be slightly positive, one of them will be slightly negative. Like it could be this is positive, this is negative, but it doesn't really matter. So that means, it just means this is a polar bond. Okay, so this is a polar bond because they have different electronegativities, so they don't share electrons equally. So if they don't share electrons equally, then we have two possibilities. Is that if we have a polar molecules, that means these bonds won't cancel each other out, so you have a bent shape. And I'll use SO2 as an example. This is what SO2 looks like. So SO2, so it fits the formula of ZX2, so ZX2. So as you can see, I have polar bonds, but because I have this guy up here, this has a bent shape. So that means this SO bond and this SO bond cannot cancel each other out, and the polarity remains. So if it was a non-polar, that means the bond will cancel each other out in the form of CO, like say for example CO2, like for example this one. So this is a polar bond, this is a polar bond, but because they have a linear shape, the polar bonds will cancel each other out. So sorry, the dipoles will cancel each other out, which means you have got a non-polar molecule. Okay, so you don't need to explain it. So factors that affect polarity, so always remember this. You need to have polar bonds. This is so important, people always forget this. Polar bonds, what does that mean? That comes from significant difference. Significant difference in electronegativity. Okay, so that means you have bond dipoles. You form bond dipoles, and that's going to give you the difference in the charges. Okay, and then the next thing is the shape. If you have a symmetrical shape, and then the bond dipoles will cancel out. If you have an asymmetrical shape, the bond dipoles don't cancel out, and it will remain polar. Okay, so that's pretty much all there is. They're just trying to ask you the same type of question but change your wording. So here you go. If it's polar, that means the bond is polar. Significant difference in electronegativity, so they're not arranged symmetrically, and they can't cancel out because the dipoles don't cancel out, so it's going to be polar. And if it's in a linear shape, the dipoles formed by different electronegativity to cancel, therefore it's going to be non-polar. Okay, so just same type of question, just different wording. Okay. Oh, calculation. So here we go. We got a calculation question. All right, so let's have a look at this. So the best part with this type of question, you just look at, just make sure you know what you're calculating. So we're calculating the mass of sulfur. So we need sulfur, which is this guy. Sulfur dioxide can be made, blah, 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 blah. Okay, not important. 740 kilojoules, the enthalpy is -296. Okay, so the first thing that we have to look at, calculate the mass of sulfur. I need the mass of this. 740 kilojoules of energy is released. So let's have a look at this. What does this equation actually mean? That means if I burn 1 mole of sulfur, I release -296 kilojoules. Okay, and then you may go, what about the oxygen? What about sulfur dioxide? Not interested in them, because I'm interested to calculate the sulfur, the mass of sulfur. So 1 mole of sulfur gives me 296. Okay, now I know I produced 740 kilojoules. That's right here. So how many moles did I make? How many moles did I need for this to happen? So you use 740 divided by 296, and that's going to give you 2.5 moles. So how heavy is 2.5 moles? So remember, N equals small m divided by big M. So you know the molar mass, which you know this guy. You know the mole. How do we figure out the M? It's just N times big M, which is 2.5 times 32.1, which will give you 80.3 grams. Okay, so let me just quickly run these numbers in my calculator. 740 divided by 296 and times 32.1, 82.3. Okay, so pretty straightforward, nothing too tricky here. Yep, that's end of question 2. Question 3. Okay, so enthalpy. So calculate blah, blah, blah. Do I need to calculate anything? No, classify the reaction as endothermic or exothermic. Okay, so if you just look at this, that's a negative number. Negative number, that means is exo. Oops. Exo. And they say give a reason. Well, this number is negative. Done. Reason. Completed. Complete using labels, energy diagram for the combustion of octane. So we're still looking at this. Okay, so this is an exothermic reaction. Exothermic reaction, that means your enthalpy at the end is going to be, so showing the product, so I can just label products. I mean, if I really want to be thorough, I'll just put 16 CO2 plus, not 16, I'll just put CO2 plus H2O, that's my products. This is this is reactants, which are these reactants. I can't be bothered writing them, just these guys up here. From here, from the difference between the two lines, this is the change of enthalpy, which is negative 11018 kilojoules per mole. And from here to here, they didn't say label it, but I did anyway. This is the activation energy. Okay, so if you get asked for an endothermic question, it will look like this. Okay, so this is your reactants, this is your products. The difference between the two lines is your change of enthalpy, and then the little hump that has to go over is the activation energy. Okay, not a difficult question. Next one, ethanol is a liquid at room temperature with a boiling point 78.4 degrees. Whether the change of ethanol from liquid to gas is endothermic or exothermic. So if going from liquid to gas. Okay, if you're going from liquid to gas, I mean, I was teaching my year 9 so it's not long ago. You know, this is what a liquid will look like. This is what a gas look like. So to go from that to that, can you see we have to bond? We have to do what we call bonds breaking, because we have to break. We have to overcome the intermolecular forces. Intermolecular forces to physically separate the molecules apart from each other in order to make this happen. So to overcome so they're not going to do it on their own. So in order for this to happen, energy must be absorbed. Okay, so you absorb energy to break the existing force of attraction, which is the intermolecular force, in order to separate the particles away from each other. Like, say for example, you in your class, you would have gone through your schooling years with at least hopefully one of these classes. Well, it's not ideal, but you're gonna have a few people in your class that will cluster together and just talk and get on teachers' nerves, and then your teachers one day have enough, they go, all right, you go away, you sit over here, you sit over there, you sit over there, you sit over there, as far away from each other as possible. And so that is energy being absorbed from the teacher. You're getting the energy from the teacher telling you off, and then you overcome the force of attraction that's holding the friends together, and then they're separated. Okay, so energy must be absorbed, the yelling from the teacher being absorbed, and they're like, oh my god, I have to separate, and then they sit in the corners. Okay, so if energy is being absorbed, this is endothermic. All right, nice and easy. Next one, the chlorination of ethane can be shown by, so calculate the bond enthalpy. So whenever you see this table, always remember the change of enthalpy is the total of bonds breaking minus the total of bonds making. Okay, so what do we need to break? So you can look here, C2H4. So they draw it for you. So this is C2H4. How nice of them. They actually draw that for you. This is ClCl, and this is the CH. This is that one. Okay, so bonds breaking. Now, they actually gave you the question. They gave you the delta H, which they gave you this. They want you to find CCl. So let's just draw it out really quickly. So we want to break. I'm just going to rewrite this, just putting the formula in, plus ClCl, turning into CCH. I'm just going to copy exactly how they draw it. ClCl. Okay. Now, there is an easy way to do this. Instead of breaking everything on this side and remaking everything on the right hand side, but I'll just do it the long way, because that's what, if you come to here, you're probably struggling. If you're struggling, I'll just teach you a way that always works. Okay, so you don't have to think about, all right, can I use the easy method or can I not? Okay, so what you could do, so this side is your bonds breaking, this side is your bonds making. Okay, so we have to break everything on the left hand side and remake everything on the right hand side. So what are we breaking? So we're breaking CH bonds. You're going 1, 2, 3, 4. You're breaking CH bond times 4, and you're breaking a CC double bond times 1. Okay, so that's going to be CCH is going to be 414 times 4. CC double bond 614 times 1, which is just by itself, and that's going to give you 414 times 414 times 4 plus 614. That's going to be 2270. So that's bonds breaking. On the bonds making, what did I make? I make CH bond 1, 2, 3, 4 CH bonds. Now this is what I meant by the easier method. Can you guys see that you're not actually breaking them because they didn't break and they're still there? But mathematically, it's the same thing. So I will really doubt if they count, if they punish you. Because when I teach my guys, especially the people in my class that are struggling, I just always say, look on the left hand side, break everything. Look on the right hand side, make everything. Okay. Oh, and then I just realized I forgot the CCl. Okay, so it's the ClCl. I need to break the ClCl bond as well, which is going to be 242. So if I add up all these numbers together, that's going to give me 414 plus 242, which is 2512. Now, if looking on the right hand side, I need to make 4 CH bonds. Then I need to make a CCl bonds, 2 CCl bonds. Then I also need to make a CC single bond. So there's 1 CC single bond, which is 3, 4, 6. The numbers are all up here if you're wondering where I got them from. And I need to make 2 Cl bonds, but I don't know what they are. Why? Because I'm trying to figure out what CCl is. Okay, so how do we do this? All right, what is the enthalpy? This is going to be -148, which is coming from here. All right, so let's just calculate. So if I don't know CCl, I can just make it X. Okay, this is 2X. CCl I don't know. So if I put everything back in here, let's just do the bonds breaking part. So this is 414 times 4. Let me just do the, let's just add them up first. Let's just add this up. So 414 times 4 plus 346. So on the right hand side is 2202 plus 2x. Okay, because I don't know what to CCl is. Okay, so bonds breaking, that means 2512. Look at this formula: 2512 minus 2202 plus 2x equals, what does that equal? The change of enthalpy, which is given to you before, so it's -148. And then if you break it, if you do your simple mathematics, if you can rearrange the equation, you will find that your 2x equals to 2512 minus 2202. Then move to the other side, and 148. Wait, did I mark it up somewhere? 856. CH2Cl. Wait, I'm missing a number somewhere. 414. Bonds breaking is 1 plus 242. That's right. And the other side is 346 2x. 414 times 4 plus 346. I'm just crunching numbers in my calculator. Plus 2x. So 2512 minus 2002. Yep, so this is going to be 658. All right, so 2x equals 658, and x will equal to 658 divided by 2, which is 329 kilojoules per mole. Okay, so this is a harder version of the question, but with this type of question, you always want to just make sure you want to write down the equation first, and just ask yourself, what am I breaking, what am I making? Get the two numbers down. And normally sometimes they ask you to figure out the change of enthalpy, but in this case it gave you the change of enthalpy and asked you to figure out one of the bonds. So you just write down the equation as you see from here. Sorry, it's a bit messy, but you can write down the equation from here, and then this is pretty much just that. So 2512 is the bonds breaking. This thing that I'm highlighting right now is bonds making. Negative 2148 is the change of enthalpy, which is given in the question, and then just use your mathematical skills to figure out what X is. Okay, and if you can't do that part, like say the last part, if you know the chemistry but can't do the math, maybe write down the equations and go ask your math teacher, because you're year 12, you shouldn't be struggling with that at this level. Okay, is this the last question? Yay, last question. Okay, so ethanol can be burned as a fuel. Amazing. Complete combustion. So 1.5 kgs of ethanol, which is this guy, is burned completely. It releases 40,600 kilojoules of energy. Uses this information to calculate the change of enthalpy. Okay, so so this is where you go, all right, 1.5 kilograms. So remember, whenever we see kilograms or grams, we don't like that. We want to convert that to moles. So N equals small m divided by big M. So whenever you see grams, just turn that to moles in chem. You're unlikely to get that wrong, okay? Because that's normally what you're required to do, okay? So 32.61 moles. So think about this. If I burned 32.61 moles of ethanol, I got how much energy? 40,600 kilojoules of energy. What is it asking you to do? They're asking you to figure out how much energy would I release per 1 mole. Okay, so you simply just go 40,600 divided by 32.61. You should get, let me just do this really quickly, divided by 46, and then divide 40600 divided by answer, and that will be 1245. Oops. 1245 kilojoules per mole. Okay, but remember, this is an exothermic reaction, so it releases 40,600 kilojoules. So the enthalpy will be negative 1250 kilojoules per mole. Okay, you may go, but you wrote 1245. Yes, 1250 is rounded to 3 significant figures. Now, a few things you need to have. You need to have the correct unit, because that's a unit for change of enthalpy. You need to have the correct sign, because it says energy has been released. So you need to write that down, and then round to 3SF. Okay, in order to get your excellence. Okay, so this is the 2020 2.4 exams. Hopefully that has been helpful. Now, from now till the school exams, I will go through all of the 2020 exams for level 2, level 3, and level 1 as well. Okay, so hopefully this has been helpful. If you could subscribe, if you haven't, leave a like, and I'll see you guys next time. Bye bye.